So I'm going to talk a little bit about how we attach chemical species to objects and how we write spatial transport flux reactions between these species located at different objects. So this example is rather verbose. Just to illustrate a few points, we could actually write this a lot more succinctly, but I just want to illustrate a few points. So basically what we do is we create a number of different classes or types of objects here. So I made an A here, and this is this we can basically treat as a background or an environment object. Then I made a couple different ones. I made a producer and a consumer, and these guys are going to have their uh, and we're going to write a secretion and an uptake flux between these guys and the background objects here, A. And then I'm going to make a couple other ones, a source and a sink, and what we're going to do here is we're using the standard antimony syntax where we're going to fix the values of the species located in these objects. So we use a $sign S1 equals blah and $sign S1, so this just initializes the 0. So the first thing we notice is attaching objects. All we have to do is we have to do a species equals, and we give it a list of strings there. And each one of these strings corresponds to an antimony species definition. Internally, this actually gets compiled to an SPML object, but not really relevant. So this class A has a species S1, S2, S3 hooked up to it. The producer one, we have S1, and we initialize this value as 200. So whenever we call reset on this object, this 200 gets set back into the value there. And then, okay, great. So we went ahead and defined these types. So now we can write fluxes between these types. So the basic flux, this is a Fickian or a standard diffusive passive flux between these objects. So basically this says is whenever we have an object instance of A, or actually two object instances of A, that have a species S1 on them, we will initiate a passive transport at a rate of k equals 5 with a decay of 0.1. Now we have a secrete flux. So when we have, so this is a forward-only flux. It's a non-reversible, unlike the standard flux one. So what this does is we have a producer object here and an object A. You know what? Why don't I go ahead and run this, and while I'm talking, and I'll show you running there. So we have the producer object A and S1. So what this does is this will produce, or actually technically it will consume the species S1 at the object at the first site, and then create some amount of the substance at the second object of the species S1 at a rate of 5. And this last one here, the target. So what this does is we will continue producing, we will continue secreting from the producer up until its value goes back down to 0. Now uptake is the opposite of a secretion, where what we do here is we go from A to our consumer, species S1 at a rate of 10, and we will continue uptaking this amount. We will continue uptaking from its surrounding objects up until the value at the second object reaches that threshold of 500. Now we got our sources and sinks. So what I've done here is I've set these as boundary conditions. S1 is a boundary condition. So when I do a secrete there, that will produce at a constant rate, but it will not consume anything. Because I've set it at a boundary, because I've set this as a boundary condition, the value of the source object or the value of that species at the source will not change. Similarly, if I define these sink objects that have a species S1 hooked up to them, when we do that flux, we will consume at the source, but we won't actually change that value. So what we're doing here is, because this is a flux, we're moving, or actually we have this, because this is a reversible reaction, and the boundary is set on the sink. This will effectively consume S1 at whatever instance of A we have, and it will not change the value of any object that is an instance of sink. So then we create a lattice of these, just use the lattice initializer. And then what we do here is we go ahead and grab the objects at the corners. So we have grab the object at the left part, right part, and we change it to be a producer, consumer, source, sink, and reset the values. And I just hooked up a little key event, so I can just press the X. Oops. Change that. Wrong window set, so I can just press the X, and that would reset that. So now we've actually made our model there. So we can see that we've set the values at the corner to, we've set the types at the corner to be a sink type. Then that left guy, we've defined that to be a producer, and we've defined this guy to be a consumer. So I can simply reset the values there, and because we've defined that as a source with a boundary condition, that will continue producing indefinitely there. And we've defined these corner ones as sinks, so they will act as continuous sinks. And then, so we can see that one. So we can notice. Oops, let me go ahead and stop this. Reset that. So this is the initial condition. So we have that initial value set pretty high up there. And you notice when I run this, what happens? Okay, you see that flicker. So because we've defined that as a non-boundary type. So that means that flux reaction that occurs there, that consumes material there and produces it in its surrounding environment, in its surrounding neighbors. Similarly, because that is not a boundary species on the consumer there, we consume material around these surrounding objects and then we move it to there. So if species are not boundary, then their total amounts are conserved. If they are set as boundary, then the total amounts are not conserved, and we can have a true source and sink there. So again, this, oops, let me switch there. So this all, it runs. This is all running in real time, and we can have a lot of fun with this. And it's really up to the users to come up with all sorts of really fun applications that we can do with these sources, sinks, and generalized boundaries. Thanks.